some doubts and all. Okay, good evening friends.
Good evening.
Ha.
Good evening.
So here we go. Okay, now straight away handle this problem first.
Make it.
It's the biggest. Oh, sorry, it's not 100%. A uniform rod is made to lean between a rough vertical wall and the ground. Show that the least angle at which the rod can be leaned without slipping. So it's ನೇನಿಲ್ಲ ಫಸ್ಟ್ ವಾಲ್ ತಗೋರಿ ಗ್ರೌಂಡ್ ತಗೋರಿ ಒಂದು ಲ್ಯಾಟರಲ್ ಡ್ರಾ ಮಾಡಿ ಎಲ್ಲ ಫೋರ್ಸಸ್ ತೋರಿಸ್ರಿ and say it is in equilibrium. It automatically will get the answer. Nothing. Oh, mu, what to do? That all you should not worry. Oh, a ladder is there, it is leaning. That's all. Over. Write all the forces. So first thing is, whatever condition is given, write that condition. Ladder which is leaning. So, what are the forces acting? One force will be acting like this, and there is friction here. So, therefore, be frictional force up. And here also, there will be frictional force like this, and there will be one more force like this. Okay, so they said this is between the mu1 is the coefficient between rod and wall. So this one will be R1, reaction R1, this is reaction R2, and here mu1 will come into picture. This is R1 and this is F1 force, frictional force. This force is F2 frictional force. Reaction is R2, and the weight rod will be done. Okay friends, I hope you have drawn this diagram.
Yes sir. Sir, mu are different sir for both.
Yeah, so mu between the wall and this is mu1 and here it is mu2.
Yes sir. Yes sir.
That's what they have. Okay, and they have asked us to say theta is equal to tan inverse of 1 minus mu1 mu2 divided by 2 mu2. So this theta. So we have to prove theta is equal to tan inverse of 1 minus mu1 mu2 divided by 2 mu2. This is what we have to prove. Correct now? My memory is okay. 1 minus mu1 mu2 divided by 2 mu2. The least angle at which the rod can be leaned without slipping is given by theta is equal to 4. Okay, so from the whatever they have told, you just draw these things first. Okay, then automatically you see, you say it is under equilibrium. You get the equilibrium conditions here. Over.
Yes sir.
So one by one. So you will get here F1 is equal to mu R1 and F2 will be equal to mu R2. Straight away you will relate these two equations, these two. And then for the summation F condition, summation Fi condition, so here W is down and these two are up. So what is it now? What does it imply? W is down and W is equal to F1 plus R2. Both are up. Okay, and then as far as the horizontal reaction is concerned, so okay, so R1 will be equal to F2. So all those conditions are clear here. R1 is equal to F2 and W is equal to F1 plus R2. All those conditions are. See, whatever data they are given, write that diagram and write your abstractions from this. So you have to get the theta there into picture. So you can take moment about this point or this point. One of these points you can take the moments. So theta is here, but take the moment about this point. So you take the moment about this point, then so you might have to assume the length of the ladder be L. So taking the moments about this point, point 1, then F2 into L sin theta. What will this do? This F2 will turn the ladder like this. Okay, and R2 will turn the ladder ulta. Into L cos theta. And W will turn the ladder like this. Okay. And what will W do? W will turn it like this.
It will be 90 degrees.
So F2 is going to turn like this, W will also turn like this. So W into L by 2 sin theta. This will also turn like this. About the point 1. And this will be equal to 0. So we get F2 tan theta, we get plus W by 2 tan theta, we get, and this is equal to here R2. And we want mu2 to come. So R2 is equal to F2 by mu2. So this is mu1 and this is mu2. R2 is equal to F2 by mu2. So the equation we have to eliminate W also. And W is equal to F1 plus R2. All of you are solving?
Yes, sir. Done, sir. Done.
Golden silence.
Done. Done, sir.
Okay, wait, I am also doing
Done.
Hey, you are all youngsters, man. You are 17 years. I am 58. You have to do it on the board. Okay, till this point. So you have to fill in what is that? Okay, friends?
Yes, sir.
Are you able to prove it?
Yes, sir. Yes, sir. Yes.
Fine, that's up. So, see, the moral is, the problem is given. Don't start worrying, oh, what is this mu and all. Don't put your eyes on so things like that. A ladder is leaning. So, you take the cue. From whatever you understand, you write that first. See, whatever you are, oh, what is that mu 2, mu 1, don't bother. Write it. Then automatically it will take you towards the answer. You don't have to get the answer. It will drive you towards the answer. Right? That's all.
Yes, sir.
So R1, R2, mu1, mu2. Okay, friends?
Yes, sir. Done, sir. Yes, sir. Yes, sir.
Okay. So just that when rigid bodies will touch upon these concepts. So power is something that rate at which work is done. Just a recap. So P is equal to F bar dot V bar. Just a recap of power. Okay. So that we have to use work energy theorem here. So work energy theorem, if you remember for translatory motion, we said the work done by net force. The work done by net force will result in what? Change in the kinetic energy.
Yes.
I hope all of you remember this.
Yes.
So here work done by net force ke badle work done by net torque will result in change in the rotational kinetic energy.
Rotational kinetic.
Only thing is now forces are acting, so both the things will happen. There will be change in translator kinetic energy and there can be change in rotational kinetic energy. Depends upon which is the point of rotation we choose and etc. etc. Okay, so that is basically the idea behind this. Okay, of course there are some considerations here. I hope you have read this. To calculate this equation is applicable to all inertial as well as non-inertial frames. So when we say net force, we have said net force. We didn't say net conservative force, net non-conservative force. We did not do anything like that. Okay. To write equation of work energy theorem, energy must be relative to the frame under consideration. Very important, because kinetic energy will depend upon the frame of the work. To calculate work done, only the physical forces in the inertial frames and all the physical forces as well as the pseudo force in non-inertial frame and displacement of the point of application of these forces relative to the frame under consideration. So you should consider all the forces, inertial, and if you are non-inertial, that means you will first apply the pseudo and then you will convert it into inertial frame and then you can apply the Newtonian equations.
Yes, sir.
For a system of several bodies, the corresponding equation of work energy theorem can be obtained by applying the theorem for each individual body and then by adding all of them. This is a common feature in all the things. So, supposing you get stuck whether I should use translatory, whether I should use rotational, etc., etc. Then you simply look at the rigid body as consisting of many particles and you work on one of the particles. That will give you an idea what to do.
Yes.
here the term summation 1 to 2 equals the work of all the forces acting on various bodies irrespective whether the forces are internal or external from the point of view of the system under consideration. Okay, so work done by internal forces as well as the external forces must be taken into consideration. See, internal forces, if you add, the internal forces will cancel. Hello?
Yes, sir. Yes, sir.
But work done by that, you have to take that into consideration.
Yes, sir. Yes, sir.
Okay, please keep this in mind. Work done on the system.
Yes, sir.
Right? Work done on the system. See, supposing I am lifting this here. So there are two forces acting. One is the gravitational force is down and whatever force I am applying is up. So what is the work done on the system? Okay, so work done by my hand is F into x. Work done by the gravity will be minus mgx. Both of them are acting here. So you have to consider the effect of both these forces, and that will be equal to the change in the kinetic energy.
Yes, sir.
Okay, like that. Okay, we have worked on that. Similarly, you have to work it. Here the term summation W1 to 2 equals the work of all forces acting at various bodies irrespective of whether the forces are internal or external from the point of view of the system under consideration. In systems of several bodies interconnected by links of constant length, inextensible cords, rods, etc., or the body in direct contact, the total work of the internal forces vanishes. If it is connected by rods and things like that. The work done by internal conservative forces can be accounted for by decreasing the corresponding potential energies. The terms K2, K1S is the total kinetic energies of all the bodies in initial and final stages. Okay,
yes.
Now don't try to by heart all these things. These are just that it is mentioned here. So when the situation is created, you just see which force what work is doing. F bar dot dx.
Yes.
That's all.
Okay.
So what happens? What is that F bar? It can be internal force, it can be external force, it can be the pseudo force, whatever it is. F bar dot ds is the work done by that force. Because the very definition of work done is like that. See, when we define work done, work is said to be done when the point of application of force displaces. And there is a component of force in the direction of displacement.
Yes.
So when we said force there, we did not say what type of force. So that should give us the idea that yes, we just have to work like this.
Yes, sir.
Clear?
Yes, sir.
So make your life simple. Don't try to by heart things. So conservation of mechanical energy. So conservation, whenever it comes, then you see the conservative forces have to be taken into consideration.
Yes, sir.
Okay, work done. The work of conservative forces equals the decrease in potential energy. This is well known fact. When a single body moves or a system of rigid body changes its configuration under the action of conservative forces, and non-conservative forces are either present or not, or if present, no work. The work energy principle can be stated as so and so. So that means now potential energy means it is only because of the conservative forces.
Yes.
Keep this in mind. Okay?
Yes.
Right? So therefore, if the work is done by the conservative forces, either it will increase the potential energy,
Yes.
and if the potential energy of the system increases, its kinetic energy must decrease.
Yes.
Okay? So now here be careful. So now here if both the forces are there, conservative or non-conservative forces. So you work separately. Work done by conservative forces. Okay, what will the work done by conservative forces do? If it increases the potential energy, then it will decrease the kinetic energy, or vice versa.
Yes.
But work done by the non-conservative forces.
Yes, sir.
Hello, work done by the non-conservative forces. What will that do?
It will only increase or decrease kinetic energy.
It will only increase or decrease the kinetic energy. Wonderful. Got it, all of you?
Yes, sir. Yes, sir.
Do you all agree? Demon told it will either increase or decrease the kinetic energy. Do you all agree? Friction is a non-conservative force. Will it increase or decrease the kinetic energy?
Yes, sir.
It will do both. Depends upon the situation. See, now earlier problems, when the disc was rolling and when you put it on the ground, right? The disc was rolling when you put it on the ground. What happened here? The frictional force increased what?
Accelerated.
It increased the translator kinetic energy. But it decreased the rotational kinetic energy.
Yes.
Isn't it? So please keep that in mind. Because friction will also do positive work. It's not only that it does the negative work. Okay? Fine.
Yes, sir.
See, you have broader spectrum. Don't try to generalize and start biting, and I please don't generalize anything unnecessarily. Situation is there, you just apply science. Now, solve this problem. A uniform rod of mass m, length L, pivoted at point O is rotated in vertical plane. The rod is held in horizontal relation. Find the distance x from the pivot from the mass center C of the rod, so that the angular speed omega of the rod through the vertical position is maximum. ಈ ಬರ್ದ ಈಗ ನಿಮ್ದು ಕ್ಲಾರಿಟಿ ಸಿಗ್ತದೆ ನೋಡಿ ಈ ಪ್ರಾಬ್ಲಮ್. So now you are seeing a problem where the rod is pivoted at some point and you have rods on both sides.
Sir, length is I, sir.
Did they give?
Yes, sir. Yes.
They given? Length, mass m length. This distance is x. So the rod was like this, now the rod is like this. So here, the kinetic energy of translation is 0, the kinetic energy of rotation is also 0 at this point. And at this point it has both. At this, when the rod is like this, what is the total energy of the rod with respect to this point?
mgx.
mg?
No, sir.
Because the rod is going to come down like this.
So it will be half into.
Because from here to here it is x.
Yes.
Okay. So this
mg
one,
by 2 plus.
so this will be what? L by 2 minus x. This point.
Yes.
Isn't it? L by 2 plus x. Isn't
Yes.
it? So what will be the potential energy of this? mg into L by 2 minus x at that position.
The plus x.
Plus x. Come on, don't simply copy it.
No, sir.
What will be the potential energy of the rod?
mg into L by 2 plus x.
No. See, you use the concept of center of mass. The entire mass is concentrated at the center. Now this center of mass will come here. So see, if the entire mass is concentrated here, then this will simply come here. No.
Yes.
Then that means its potential energy is simply mgx at that point.
Yes, sir.
And now if you say the entire mass is concentrated here and this will move down here. So that means this potential energy of the rod is now converted into kinetic energy. So you will say IC is here and this is IO. IC will be ml square by 12 and IO will be ml square by 12 plus mx square.
Yes.
Correct now? So therefore this will give me m by 12 into L square plus 12 x square. This will be I naught. So now if you say this is the potential energy with respect to this point, which point? This is x. So this has come back here. So the potential energy at this point will be 0. So it will all be converted to kinetic energy.
Sir.
So you can write here mgx will simply get converted into half into I naught into omega square.
Yes.
So half into m by 12 into L square plus 12 x square into omega square. Okay, so here permanently Mr. Yams will go here and g into x will be there. So straight away 24. Okay, we'll have to write 24 gx. I'll have to pull it that side. Divided by L square plus x square will be equal to omega square. See whether you will get this equation.
Yes.
Will get.
I got.
Yes?
X square plus 12x. 12x square.
Yes, sir.
12x. 12x. Written 12 there, no? 12. 12x. So you got this equation, all of you?
Yes, sir.
Great here, all of you. Yes. So now you have an equation for a omega is equal to root of 24 gx divided by n square plus 12 x square. Question is now you should differentiate this because they have told what is the maximum omega. They are told find the distance x of the pivot from the mass center so that the angular speed omega of the rod passes through its position is maximum.
Yes, sir.
Right? So you have to now differentiate. That is d omega by dt. Differentiate n equal to 0, and you have to differentiate this equation.
Yes.
So if you differentiate this equation, then you will get the value of x. Today Arun is very confident. Kushi Okay. Anybody is having any doubt?
Yes, sir. Please explain how you wrote MGX to half I not to minus.
See what I have taken here. I have taken the rod like this. Correct. The rod is pivoted here, and its center is the center of the rod is this, and this distance they have told is x. Okay.
Yes.
So now I will take this as the reference line at a distance x from top. Okay. Now this rod, if you think that this rod, the entire mass of the rod is concentrated at the center, m, then its potential energy is mgx with respect to this reference.
Yes, yes.
And when the rod falls down, when the rod falls down, it will be like this. The rod falls down, it will be like this. So this point will come here.
Yes.
So therefore its potential energy will become 0. Okay?
So why didn't they consider transitory tendency?
See this question last time also you were all asking. In the case of
Yes.
this one, no, you are again asking the same question. This was there, this steel scale was there, and when it fell down, okay, you calculated this one. See now if you are considering this point, no, if you are considering this point, then with respect to this point, you see this entire rod has only rotated, man. It has only rotated.
Yes, sir.
Isn't it? It has only rotated. That's all.
Yes.
See, this entire mass is concentrated here. It has rotated.
Sir, in this question, sir,
Sir, if we write it about center of mass,
Then if you write it about the center of mass, see, if you write it about the center of mass here, okay, then you have to see, well, the rod has rotated about the center of mass and also translated. That is how you have to see.
yes, yes.
Okay, well, why you want to make it so tedious? It's done. Okay, friends.
yes, sir.
Please don't waste. Let's not waste time calculating. So, if you have got the final this one, we can always do the calculation around. Please.
Sir, I didn't understand.
What?
Sir, MGX.
Hey, that time you told you understood, no?
Yes, sir, but again.
See here, I have taken this. See, the rod was horizontal, man. This is the reference line I have taken. This is the reference line. So now the entire mass of the rod is concentrated at the center. So what is the potential energy of this mgx?
Okay, sir.
With respect to this reference, and when the rod falls down like this x will coincide here. So therefore the potential energy of this is mgx. Is that clear now?
Yes, sir, MGX, sir, but finally it will have some potential energy.
That is it. See, if you take this reference line, man, If you take this reference line, where it lies the potential? See, the mass was here, now the mass is here.
Okay, center of mass would be here.
See, now the body is here. The body is here. What is its, if it is height h, its potential energy is mgh. When the mass comes here, its potential energy is 0.
Okay, yes. Understood.
See, the concept of center of mass has to be used like this only. That will make our life simple. Jingala.
Sir,
Yes, sir.
Yeah?
L by root 12.
L by?
Root 12.
I think you are right. Yes, L by root 12. Dada in mathematics. Arun side.
Simple.
Simple, all simple. Correct, difficult. See, I remember my student is, mechanics was so difficult initially. Afterwards, it started becoming the easiest thing. Understand? Because there are not too many, intricate concepts. See, compared to chemistry and all, there are not so many intricate things to bother us. It was all straightforward. Problem is given, just put the free body diagram and keep writing the equations. Mechanically, you will get the answer.
Yes, sir.
Mechanically, you will get the answer. That is all. What is there in this? And these equations are not very difficult at all. In fact, mathematics equations are very difficult. You don't know how to start and where to begin, where to end, which direction to go. But here, the direction is fixed. You just go on writing the free body diagram and the forces. Yes, friends? Yeah. I think we all wrote all these things correctly.
Yes, sir.
Yes, sir.
See here, correct.
Yes.
Correct now? MGX. They have also written MGX. 24 GX. Okay?
Yes.
Yes, sir.